Hello everyone, today we are going to perform CFD analysis on this geometry. This is a 2D flow domain which has some kind of restriction or blockage to the flow. So this the height of the blockage are 0.01, 0.02, 0.03 meters, and the velocity of air are 0, this corresponding values. So this is the geometry. So these are flow velocity, which is exactly this number. So in this tutorial I have taken the height of this blockage as 0.03 meters and flow of the fluid as 0.0322, and we have kinematic viscosity of air at 30 degrees Celsius. We need to convert this into dynamic viscosity and put it in our fluent. So if we convert this kinematic viscosity of air to dynamic viscosity, it will be approximately equal to the default values provided in the fluent for air. So I have by neglecting these values, I have taken the default values of air. Has been generated in design modeler with 0.03 meter of height for blockage. So this is design modeler. 2D geometry has been created. So now close this design modeler, go to mesh, edit mesh, okay. So now this is our surface body. Now let's first go with the default mesh. So this is the default mesh. Sizing, let's give the edge sizing. With number of divisions as, let's say, 100, 80. Okay. So another mesh sizing, same number of divisions. Another one, edge sizing. This one, this 4 edges. Apply. Number of divisions 10. Now final edge sizing for these bottom edges. Apply. Number of divisions, say 5. Phase meshing. Apply. Now generate mesh. Now let's give name selection. Flow domain. Outlet. Flow domain, inlet and outlet. Okay, update, close, go to setup. Okay, so there is no gravity in the problem, so will not use any gravity. The time will use steady state. Go to model, change this model from laminar to k epsilon turbulent model, scalable wall function. Okay, now material, that is the air is used, so we'll use this default properties of air. You Yeah, the velocity of air, close. There is nothing to do here except air, material name air. Okay, now boundary condition, the inlet. For the inlet, for the purpose of getting Reynolds number 200, that is 0.032. Okay, since this Reynolds number is 200, which would be a laminar flow, so I'll just change this viscous from turbulency to laminar flow, so because the Reynolds number is 200. Okay, so now at boundary condition, now the inlet, velocity will be 0.0322, 0.0322, so 0.0322. Okay, this is outlet, zero gas pressure, outlet. Okay, so at this point we have set up our boundary conditions. Now let's just initialize the problem and run the solution. Before that, we'll change the residual as well from 10 to the power of -3 to, let's say, 10 to the power of 6 for more accurate results. Okay, now initialize. Okay, initialization has been done. Before that, let me just save the project, save, say some 1 2 3 and save. Okay, now let's go to run calculation. I'll say initialization for 1000, calculate. Okay, we have, so now we have, at this point we have reached our residual. You can see at 477 iteration it has reached 10 to the power of -7, -9 and -9. So we have reached it. Solution is completed. Now let's save the project one more time. Now close Fluent. Okay, now solution has been completed. Let's review the results. Let's set as the contour, symmetry 1. Look at the velocity. So this is the velocity. So due to this blockage, the flow of the fluid gets some wavy structure after passing through this constriction. Okay, let me just increase this contour, number of contours. Let's see what happens to the pressure. Increase this to 50.